Welcome back, everybody, to our last session of the conference. I think you all know the drill at this point. We'll start out with our 3 15-minute talks, then we'll have some group discussion, and then we'll finish it off with a lightning round. So I think we can go ahead and get started. Go ahead and take it away, Travis. Travis will be talking about stellar age dependence of the planet radius gap.
Okay, thank you, Tim. So first, before I start, I'd just like to say a word thank you to the coordinators of this conference for inviting me to give this talk. This is all work that I've done with collaborators Dan Huber, Jen Van Saters, Eric Gaidos, Jamie Tyre, Lauren Weiss, and Adam Kraus. So here's a plot from Fulton et al. 2017 showing the number of planets per star on the y-axis or occurrence rate versus planet size on the x-axis. And what's immediately apparent here is that there is a gap in the distribution of small exoplanets separating the super-Earths down here at about 1.3 or so Earth radii from the sub-Neptunes up at about 2.4 Earth radii. And the resolution of this gap was made possible thanks to the very precise stellar properties of the California Kepler survey. Now, a lot of work has been done on this gap in subsequent years, and a lot of questions have been asked, such as how the gap varies as a function of incident flux, orbital periods, stellar mass. And I think especially in the future, asking how it varies as a function of stellar age is going to be a very interesting area to investigate. Now, obviously, we see this gap in the distribution of small planets. So how exactly did it get there? Well, there's two competing theories that I want to discuss today. The first of which is photoevaporation, which works by taking the very high energy XUV and EUV radiation from the host star and photoevaporates planet atmospheres on timescales of 100 to 200 million years or so, which is usually when host stars are most active early on in their lifetimes. And then the second one is core-powered mass loss, which uses a combination of the core luminosity of the planet plus the incident bolometric flux from the host star and various mass loss timescales and the incident flux from the host star. And this actually results in planets losing their atmospheres on gigayear or so timescales. Now, in terms of how they actually compare to the observations, so on the left, we've got some photoevaporation models from Owen and Wu 2017, which shows planet radius on the y-axis versus orbital period on the x-axis. And the densities of planets here are plotted as the various different colors. Darker colors indicate higher densities or occurrences of planets, whereas on the right, we've got our observations from Fulton et al. 2017. And just looking and comparing these plots qualitatively leads to, well, the models and the observations match up pretty well. Now, how about core-powered mass loss? So again, I've got the models over here on the left, which now come from Gupta and Schlichting 2019. And on the right, we've got observations from Fulton and Aguirre 2018. And again, we see this qualitative agreement between the models and the observations. So then this leads to the question, well, how do we go about differentiating between these two theories if both describe the observations well so far? You might be able to think about a few avenues we can take. So number one, we might want to look at other areas of parameter space, such as stellar mass or incident flux. And then also we might want to get, for instance, more precise stellar properties. So on the more precise stellar properties front, here is a plot taking data from Mathur et al. 2017, which shows the Kepler stellar properties catalog as of 2017 and the isochrone modeled stellar radii on the y-axis versus effective temperature on the x-axis. Now keep in mind, this is before Gaia DR2 came out, and so therefore the vast majority of the constraints on these stars were actually photometric, which led to median fractional radius precisions of about 25% or so. And you might be able to notice a few interesting looking areas of this diagram. For instance, you've got some stars that are latching onto a model grid over on the hot star side. The red clump is not very well defined over here. There aren't too many subgiant stars. And then also there's this kind of strange gap in the distribution of effective temperatures. Now, how do things change when we implement Gaia DR2 parallaxes in combination with a uniform effective temperature scale? Well, we see that things sharpen up very nicely. I'm just going to flip back once more. And what you'll notice is that, first of all, there aren't too many, there aren't clear, latching onto model grid for the hot stars. There's a very clear red clump here. There are more subgiant stars, and then also we're not seeing this gap in the distribution of effective temperatures for cool stars. And what I want to stress is that we've got these 4% fractional precisions on stellar radii as compared to the 25% or so beforehand. And I also want to note that we have masses, ages, densities, and more for every single star within this diagram, so we can look at a variety of other stellar properties. Now, before we get too far ahead of ourselves, I want to take a step back and make sure that one of these properties, which I'm going to focus on for the rest of this talk, ages, is validated and well determined. So one of the ways we went about validating our ages in this catalog was to actually compare to clusters. And so there is actually one cluster, there are a few clusters within the Kepler field, but we decided to focus on NGC 6811, which has an isochrone main sequence turnoff age of about 1 gigayear or so. And so that is plotted here as this black vertical line. And then each of our ages determined for the individual stars within this cluster are shown down here at the bottom. And as you'll note, this red distribution actually represents all of those ages put together. And what you'll notice is the mode of this distribution occurs at a very similar age as the age of the cluster. So we can be pretty confident in the ages that we've determined for NGC 6811, and therefore some of the ages that we've determined for our stars in our catalog. In addition, if we want to compare to maybe one of the best age determination methods, astroseismology, we also did a comparison here. So in this plot, we've got our age derived through isoclassify and our isochrone ages on the y-axis. And then we've got literature ages, which come from Silva, Aguirre et al. 2017, which come from a variety of different astroseismic pipelines, which are indicated by these different colored points. And so this was using, frequency modeled stellar ages, and these are for the Kepler legacy sample. Now, what you'll notice is that especially for young ages, the agreement is pretty good and pretty tight around the 1-to-1 line, which is what this dashed line represents. Now, as you start to go to older ages, we start to see that things deviate a little bit more from that line. However, if you look at the range of values for each of these stars determined by the various astroseismic pipelines, typically those differences can be described by those discrepancies between the different astroseismic pipelines. Now, you might also notice that up here towards the top, there are a few points that are significantly above the line, and it turns out that these points, we've actually determined ages older than the age of the universe, because in our modeling, we use a maximum grid age of 20 gigayears to minimize the effects of truncated posteriors. And so that's why we're getting ages older than the age of the universe here, whereas we believe that a lot of these astroseismic pipelines are using a grid that goes up to about the age of the universe or so, which is the maximum age that they're determining here are about 12.5 or so gigayears. But I think overall, the agreement here is very good, especially when we're comparing ages determined just through isochrones and those determined through astroseismology. So now that we have all these shiny new stellar properties and we feel confident in the ages that we've determined, what can we learn about the planet population? So here we've got planet radius on the y-axis versus incident flux on the x-axis, and points here are colored according to the stellar mass of the host star. The solid points here are confirmed planets, whereas the translucent points are candidate planets. And if you've got a particularly keen eye, you might have noticed that there appears to be a color gradient going on in this plot from left to right or right to left, which indicates that there is a mass gradient going on here. Now, let's think about what incident flux actually depends on. It depends on the luminosity of the host star, which is dependent on the mass of the host star. And because luminosity is very strongly dependent on the mass of the host star, we kind of see this overall gradient going on here. Now that is, oversimplifying things, but to first order, that's what's going on here. Now, in addition, you might have noticed that there appears to be this underdensity of planets located here towards the center of the diagram, which is what we call the planet radius valley, which is a two-dimensional representation of the one-dimensional planet radius gap that I showed before, which separates the super-Earths from the sub-Neptunes above. And because we see that it is dependent on planet radius and incident flux, it's dependent on incident flux, and it's also likely dependent on stellar mass, this might lead us to ask the question, well, how does the planet radius valley actually depend on stellar age? So here we've got the number of planets now on the y-axis, not occurrence rate, And then on the x-axis, we've got our planet radii. Each of these ticks that you see at the bottom here are individual planet radii in the old planet distribution, which are planets that are older than 1 gigayear. And what we're interested in this plot is the relative number of super-Earths to sub-Neptunes, where we define a super-Earth as any planet between 1 and about 1.8 Earth radii, and a sub-Neptune as any planet between 1.8 and about 3.5 or so Earth radii. And these are the definitions according to Fulton et al. 2017. Now, if we do some, if we count up the relative number of super-Earths and sub-Neptunes and then do some simulations and then calculate that ratio, we end up with unity plus or minus 0.1 or so. Now, we have to compare this to the young planet distribution. So what does the young planet distribution look like? Well, we see that it looks significantly different. And in particular, we see fewer super-Earths in addition to a broader peak of the sub-Neptunes. And if we do a similar computation for this young planet distribution, we end up getting a ratio of 0.61 plus or minus 0.09, which indicates about a 3 or so sigma significant difference between the old and young planet radius distributions, or at least those ratios. So what does this suggest? Well, it suggests that sub-Neptunes are becoming super-Earths on about gigayear timescales. Now, this has important implications as to which of the two theories, core-powered mass loss or photoevaporation, is actually acting on the current planet population. Originally, we had thought that this was most likely due to core-powered mass loss, and we couldn't say anything about photoevaporation because of the 100 to 200 megayear timescales related to photoevaporation. However, some recent work by James Rogers and James Owen has indicated that this sort of that photoevaporation can act on these somewhat gigayear or so timescales. But I think it suffices to say that we are seeing this difference and that it is significant. And so therefore, I'm going to leave you with that, and I'll leave you with my summary and conclusion slide. Thank you for your time, and are there any questions?
Can I have a question? I don't know how to raise my hand.
Mm-hmm. Yeah, go ahead, Deanna.
Thank you. Thank you for that good talk. And I'm not sure if you've seen the work by Cloutier and Menu that they looked at the radius gap for low mass stars. Do you find, because they find that for M-dwarf stars that slope changes, do you find the same result?
So you're saying just with like as a function, so for the low mass stars. So in this work, most of our when we were doing those comparisons, we actually did not look too heavily at the lower mass stars. We tried, but we weren't able to determine anything definitive because we didn't have quite enough low mass stars within just the Kepler field, because there was a stronger emphasis on somewhat more solar type stars. As in that Cloutier and Menu paper, there was a heavy emphasis of taking M-dwarfs from a variety of different surveys, and so we didn't necessarily have all of the M-dwarfs to really do a good comparison, because the mass range is very large, and so trying to calculate, for instance, a slope in that range of parameter space was difficult.
Okay, thank you.
Mm-hmm.
Okay, we have a couple people who raised their hands. Well, actually, first we have a question from Raphael Luque.
Mm-hmm.
It is more challenging to detect small planets around young, typically active stars than bigger ones. How does this observational bias affect your final result?
Yeah, so that's a great question, actually. I've got an extra slide that just kind of shows a comparison of, let me actually flip here, of a comparison of the old and young stellar samples. So we were very careful to try to choose the old and young stellar samples so that they were as identical as possible to one another in terms of stellar radius, stellar mass, and stellar metallicity. And so we actually ended up using a single transit signal to noise ratio, which comes from the Kepler CDPP3 values. And so we calculated, so numbers that are higher on this plot actually show planets that would be easier to detect, for instance. And so if you actually look at these large points, which indicate the old and young samples respectively, as well as their age distributions, you can see that it isn't necessarily harder to detect smaller planets around the young stars as the old stars. And part of this is actually due to the fact that a lot of the young stars are somewhat closer than the old stars. at least within this planet population. And so therefore the noise values are relatively similar between the two.
Okay, thanks, Travis. Next, I'm going to go to Jack Lissauer.
Mm-hmm.
Jack, you should be able to talk now. Or you can type your question into the chat. Okay, well, while we're waiting for Jack, let's try the same thing with Lynn. I think Lynn,
Great,
you should
thanks.
be able yep.
I hope you can hear me. The question is whether you have a version of your HR diagram or your radius versus temperature diagram that shows explicitly what you're calling young versus old. You know, where are these stars located relative to the isochrones?
Yeah, so this is essentially what we're comparing young versus old, because we wanted to. So you know, in terms of, they have very similar effective temperatures. Obviously, the young stars are typically going to be hotter on this diagram because they're younger and closer to the zero age main sequence here. But overall, this is kind of what things look like in terms of the HR diagram. What are young versus old stars, and that 1 gigayear cut, what that looks like here.
Got it. Okay. So good to see. Maybe in the paper it shows it relative to the overall distribution, like you showed earlier. But great. Nice work. Thanks.
Yep.
Okay, I think we have time for one more question. So let's go to Carrie Liss. Can you do a similar study on just high mass OBA stars with little XUV to see if they have mostly sub-Neptunes? Obviously, those wouldn't be old stars.
Right, right. So I mean, you could, yeah, I guess I haven't thought too much about using, you know, much higher mass stars. You know, obviously a lot of the stars that were targeted by Kepler and a lot of the ones that we detected planets around were typically like FGK stars, as you can see kind of in this HR diagram here. But I mean, it would be, once we start, maybe it'll be interesting to see kind of what the future has to hold for that.
Yeah, we probably just don't have enough planets yet.
Yeah.
Okay, thank you, Travis. We're going